Perfect. All right. I'm very happy to introduce our second speaker for the last session of this semester, Jan Kronqvist. Jan is assistant professor in the Department of Mathematics at KTH, or the Institute of Technology in Sweden, and he has been there since 2021. Before that, he was a Newton International postdoc fellow at Imperial College London in the Department of Computing, and he did his PhD at Abo Academy University in Finland before that, where he has received the best PhD thesis in the Faculty of Science and Engineering. Jan is an editorial board member of the Journal of Global Optimization, which is an area he works in a lot, particularly mixed integer, linear, nonlinear programming, decomposition, also software tools and applications in AI and machine learning. And today he'll tell us about improving convex mixed integer nonlinear programming. So Jan, please take it away.
Thank you very much for this kind introduction. And I want to thank you, Elias and Alex, for inviting me to give a talk here. This is really great. And I was very happy to see how many people are listening and following this presentation. There were many known names to me here in the list of participants. I'm very happy about this. So I'm going to be talking about building upon linear MIP techniques to solve convex MILP. This is intended as being a brief overview of different cutting plane algorithms. We're going to look at some improvements and current challenges. So this talk, it is based on work that has been done over several years together with several different people. So for example, it's based on work done together with Ruth Meissner, Calvin Tsay, Andreas Lundell, Tapio Westerlund, David Bernal, Ignacio Grossman, Alireza Olama, and Eduardo Campanogara. And it's kind of bits and pieces taken from different papers, but I would say the presentation is mainly based on the following 4 papers. So I'm going to be talking about mixed in convex MILP in general. What is it about? Trying to boost your interest in this area, and also look at how we can solve convex MILPs with a focus on outer approximation-based methods. And the other half, I'm going to be talking about cutting planes. How to linearize MILP problems by generating good cuts. And I also want to argue why simply applying our favorite cuts from MILP can be insufficient. And finally, we're going to look at the cut strengthening algorithm. So let's dive into it. Here, I'm focusing on optimization problems of the following form. We're minimizing a linear objective function. We have some nonlinear inequality constraints and some linear constraints, and some variables are restricted to integer values. Here, I will define a convex instance as a problem whose continuous relaxation is convex. This can be seen as the most general definition of convex here. And if you look at some application areas, so there's a lot of applications, for example, originating from process systems engineering, process design, facility layout problems, trim loss, model predictive control, and many others. But recently, there has also been a spike in the interest in machine learning, as all of you know, and I would like to claim that many of these problems are really convex MILP problems, but unfortunately they are seldom solved directly as such. So for example, clustering, sparse regression, and sparse optimization. And the reason I'm saying they are not always solved as convex MILP instances, these problems tend to be huge in size, and actually solving them can be quite challenging. But I'm hoping that as we progress in convex MILP, we will also see more and more successful applications in this area. And now to solve these problems, we typically need to make a few assumptions on the underlying problem to be sure that our favorite algorithms work. So I said that it's convex if the continuous relaxation is convex, but typically we also require that the actual functions GI, that these are convex and at least once continuously differentiable. We can relax this slightly. We can, for example, consider pseudo-convex locally Lipschitz continuous functions. I just want to mention this. I'm not going to go into details on this. If you're interested, please take a look at the following paper. Furthermore, we assume that the linear constraints gives a compact set. Basically, we care about the search space being bounded. And finally, we also require that fixing the integer variables to any feasible integer assignment results in an NLP problem that satisfies a constraint classification, typically Slater's. And out of these, number 3 is kind of the most difficult to being able to check in advance. But if we assume these properties on the problem, then we know that our favorite algorithms will converge for this type of problems. So let's look at how we solve them. So I would like to think of it as 2 main approaches for solving convex MILP. So first of all, we have nonlinear branching bound. This is very simple, exactly what you would think. Instead of, we take the concept directly from mixed integer linear programming. So we relax the problem, solve a convex MLP at the node, branch, maybe we add some cuts, and we continue branching and adding cuts. And the other type of algorithms, I would like to call these outer approximation-based algorithms. This is a little bit controversial because there is a specific algorithm known as outer approximation. But I think there are several algorithms that falls under this umbrella term. Therefore, I'm referring to them as outer approximation-based. Here, the goal is to construct an equivalent linear problem, one that gives you an optimal solution and also proves optimality. And there are several different algorithms, for example, extended cutting plane, extended supporting hyperplane, generalized benders, outer approximation. There is single and multi-tree variants of these. And by single tree, I basically mean you do branch and cut. And I will be focusing on outer approximation-based algorithms. And to motivate this, I want to show you a benchmark from this paper we did back in 2019, where we looked at 406 convex MILP problems. And these performance profiles shows how many instances the different solvers are able to solve as a function of running time. And here I don't want to point at any specific solver, but what I want to highlight here is that the 4 top solvers, they're all based on an outer approximation concept.
And so, Jan, there's a question in the chat for the
Oh.
previous slide, I believe. So Mark Stone asks, shouldn't it be sufficient that the entirety of the constraint set is compact, i.e. including g of x less than or equal to 0? I think this is on the previous slide of your assumptions.
If you, for example, focus on, if you do branch and bound, that is sufficient. In some of the outer approximation-based algorithms, it is not necessarily. It can be sufficient. For example, for this to be compact. But then you need to make sure, eventually you need to be sure that the linear relaxation is bounded. That is basically the property that you need.
Okay.
So but if you are doing nonlinear branching bound, you don't really need to worry about that aspect.
Okay. I think this should address Mark's question. Mark, if you have follow-up, please feel free to ask in the chat.
Yeah. Thank you. So I also wanted to just take this opportunity to also say a few words about our solver shot that we have been working on now since 2015, which is an open source solver for MILP problems. It's available in GAMS, but you can use it also from Pyom or Jump and also as standalone. I will not go into details of the solver here. I want to market it a little bit and show it to you. And I want also to mention that it's not based on any single algorithm that I'm presenting in this talk. It kind of combines different algorithms and uses a bunch of different techniques and tricks, reformulations, bound typing, and a bunch of different things. But if you're interested, please take a look at the following paper. Okay, so I want to kind of show you the main idea behind outer approximation-based algorithms. So assume that we have a nonlinear constraint of this form where the function g is convex. Then due to convexity, we know that the following inequality holds, basically meaning that if we linearize, we take a first order Taylor series expansion of the nonlinear function, then that will underestimate the function and giving us an outer approximation in this case. So given a set of points x1 to xk, we can very easily form an outer approximation of the feasible set of the constraint by simply generating these cuts. And these cuts are often referred to as gradient cuts. So the nice thing is that this is very simple. Just any point, this gives us a valid outer approximation. Okay, so we can now use this to linearize our MILP problem. So now take this finite set of points. We can linearize the MILP problem by generating gradient cuts for the nonlinear inequality constraints. Okay, this is nice. And the nice property here is that even if we have now linearized the nonlinear constraints, we know that this will give us a lower bound on the optimal objective value because we are looking at an outer approximation of the feasible set. But a very important property that is described in this paper by Fletcher and Leifer from '94 is that if we choose these points x1 to xk wisely, then this mixed integer linear problem, it will have the same minimum and the same minimizer as the original MILP problem. If we are not that wise in choosing the points, we still obtain a valid lower bound. But the important thing here is that we can exactly solve the convex MILP problem as a linear MIP. And I want to show you a little bit how this can be done. So I want to show you what I consider to be the simplest algorithm for solving convex MILP problems, the extended cutting plane algorithm. And here I have even simplified it a little bit more. But basically, you can start off at any point, generate some gradient cuts, solve this MILP relaxation, and you take the minimizer of that as the trial solution. If it doesn't satisfy the nonlinear constraints, you continue and repeat this procedure. If it satisfies all of the nonlinear constraints, then you're actually done. Then you have obtained the global minimizer of the problem, or a global minimizer of the problem. So it's a very simple algorithm. It generates a sequence of trial solutions with improving lower bounds on the optimal objective value of the MILP, and it converges towards the optimal solution. But here I want to mention this thing that if you implement the algorithm exactly as I have written it here above, then this can be terribly slow. It can basically run forever for relatively simple problems. But having said that, it's very important also to mention that in a smart implementation, this can work great. All you need is you need to use a few clever tricks and a good MILP solver, and this works like a charm. So the basic algorithm isn't great, but with a very few small tweaks, you can really make this work very well. And this is also described a little bit more in more detail in the following paper. But an important thing to mention here, which is a drawback of this algorithm, is that the gradient cuts that we are generating here, they can be very weak. And I like illustrations. So let's look at the following example where we have three nonlinear constraints. The feasible set of the nonlinear constraints are here shown by the light gray areas, and the intersection is the feasible set of the continuous relaxation. X2 should be integer. So now if you start the ESH algorithm, so in the first iteration, we can either solve a MILP relaxation where we just ignore the nonlinear constraint or provide an initial point. If you solve the relaxation, we would end up at a point out here, and then we violate the constraint, so we add gradient cuts. We would here obtain three gradient cuts, giving us an improved outer approximation. As you can see here from the figure, these cuts are not very tight here. I don't know if you can even see it, but there are three different cuts in this figure. But yeah, we continue, solve another MILP relaxation, add more gradient cuts, you continue and you continue. But the whole point that I want to communicate here is that these cuts, they are not necessarily tight for the nonlinear constraints. And here in this figure, here we have already accumulated 15 gradient cuts. You can't see most of them because most of them are dominated by some of the other cuts. So we would like to strengthen these cuts somehow and obtain a stronger linear relaxation. And a very simple idea here that we have been working on is if we take the linearization points, or we take solutions given to us by the MILP subproblem, we can project these onto the continuously relaxed feasible set, and then we get a stronger cut. Let me illustrate the idea. So in the following paper, we used a very simple procedure to perform an approximate projection. And the whole beauty of this is this approximate projection can be solved by just finding a root to this univariate function. So this is a one-dimensional root search. I would say this is computationally trivial. The function is convex, and we even have points with opposite sides. So now if we perform this root search, find a point here on the boundary, and then add a gradient cut, then we get a supporting hyperplane to the to the continuously relaxed feasible set. This is a much stronger cut than we saw before, and we can repeat this procedure. Okay, we have been able to obtain stronger cuts, but we should always ask ourselves, is this the best we can do? Are these the best cuts that we can use for solving these types of problems? And I will come back to this question in a few slides. But first, a quick summary of outer approximation type algorithms. It's a very similar concept that is used in several different algorithms, for example, ECP, OA, GDP, and LP-NLP based branching bound. The basic idea is that you approximate the nonlinear constraints by gradient cuts, and you solve MILP problems. And the nice thing here is we can use our favorite MILP solver that also uses various cutting planes internally. But it's important to realize here that the nonlinear constraints, they are typically not used then to derive integer cuts. And what I mean by integer cuts here is cuts that are intended to strengthen the continuous relaxation. And this is because when we do it if you have a basic implementation of these algorithms, then the MILP subsolver, it's not aware of the nonlinear constraints. It only sees the outer approximation that we give it. And this can result in a lot of unnecessary iterations and consequently a lot of unnecessary branching bound nodes. So we want stronger cuts, and specifically we want to strengthen the continuous relaxation. And I want to start this by showing you a second example where I just want to illustrate why we should consider nonlinear constraints for generating integer cuts and not only the outer approximation. So again, here I am assuming that y is an integer variable and that the gray lines here represent integer points or integer values of the variable. And here we have a feasible set given by a nonlinear constraint and an outer approximation of it. So let's say we apply our favorite outer approximation-based algorithm to generate the following outer approximation of the feasible set. Yeah. And if you now look at what are the feasible integer solutions to this problem? Well, those are restricted to these three lines here. And now if we really go crazy with generating our favorite MIP cuts, so we do lift and project, we will do Gomorrah cuts, we do a lot of rounds with our favorite cuts, then the best we can ever hope to achieve would be the following set here, which is not trivial to obtain. But my point here is that even this is the best we can do, but this is not actually a good outer approximation of the problem that we care about. Because the feasible solutions to our problem here is the line here and the dot here at the bottom. So the outer approximation we would like to obtain is the following triangle. Okay, how to obtain this triangle is not that trivial, and we're going to talk a little bit about this. So how can we generate strong cuts? Well, raising that question, I'm hoping that some of you are kind of thinking of lift and project. This is a natural candidate for a concept of generating strong cuts. We know that this can give very strong cuts to the problem. But to be effective, at least I think we would like to use so-called wide branch split disjuncts. So then I will not go into too many details, but we would basically then form a disjunction like this when we consider different partial integer assignments. We would kind of look at the convex hull of this and derive cuts from the convex hull of this. The important takeaway here is this is computationally very expensive. This would result in very strong cuts, but in practice, this is not really useful. So what we want to do is we want to derive cuts that are similar to lift and project cuts, but without solving the classical cut generation problem. Okay, that's a very nice idea, but how can we do so? And this remains an open question, but I will suggest one approach towards achieving something similar. And I want to start then by a simple observation that we made when we started the project. So if we now use the ESH algorithm, so we take a point on the outside, we project it onto the feasible set, then it's very unlikely that the point here on the boundary will be integer feasible. The cut will be tight at this point, but it will not necessarily be tight at integer feasible solutions. So for example, along this line or that line. So what we would like to do, if we just look at this conceptually, we would like to move this red line a bit inwards. Then we could make it tight here, but if we now can wish, then we could also slightly tilt it and move it inside. Then we would obtain the purple cut here. Okay, this is nice. In general, this is not easy to do, but for certain structure, we know how this can be done efficiently. And that was presented in the following paper that I'm going to talk more about, but I'm going to start by providing another illustrative example of the main idea. So here, the optimization problem at hand is we want to minimize this objective function with the constraints that we should be within one of these three circles. And we are here using a big M formulation of this. I think there is a question in the chat. Okay. Just a reminder. Okay. So let me continue. So here we have the problem. The dark regions represents the feasible set of the problem, and in light gray we have the continuously relaxed feasible set. Now, if we use the ESH algorithm, then in iteration 1 we will get the following cut and the resulting outer approximation. Now, this may not look like it's tight for the nonlinear constraints, but it is actually. Here, keep in mind, we are now looking at a projection of the cut. The cut is in x1, x2, and x3 space. We are looking at this in the x1, x2 space. So be assured, this is actually tight for the nonlinear constraints. But by simply looking at this, it should be rather obvious that this cut can be moved inwards. And that is basically achieved by reducing the right-hand side value here. But how to do this? That's a tricky question. And that brings us on to this disjunctive cut strengthening. And here we're going to use the following problem structure, where we're assuming that the problem contains at least one set packing or a set partitioning problem. But I'm going to be focusing on set packing. So we are assuming that we have a constraint that a sum of some binary variables should be equal to 1. Not all of the binary variables necessarily in the problem, but a sum of binary variables should be equal to 1. And this we will refer to as an exclusive selection constraint, since it only allows one binary variable to be 1. Okay, so let's look at the strengthening. So now if we are given a valid cut, obtained by the ESH algorithm, or basically any other algorithm for that matter, and the index set of an exclusive selection constraint, then we can determine a reduced right-hand side value for the cut by solving the following disjunctive program, where we are maximizing the right-hand side of the cut subject to all the original constraints of the problem, and we are considering all integer assignments, all combination of the integer variables in this exclusive selection constraint. So most of the variables are here still relaxed to continuous, but we are forcing the integer variables in the exclusive selection constraints to be integer, or we are enumerating the solutions. If we solve this, we can obtain a stronger cut that can be, in the worst case, it's not stronger than the original cut, but in practice, it can be a lot stronger. But we can do better. So first of all, we don't want to solve this problem as a disjunctive program. Instead, we want to consider this as independent convex MILP problems. We are just listing the different combinations of the binary variables and solving these completely independently. This can be done in parallel. And that gives us these coefficients BI here, which is how big the left-hand side can become for this fixation of binary variables. The nice thing is, if we solve it in this way, it's not only more computationally efficient, I would claim, to solve it this way, but also we can derive a stronger cut. Because now, when we fix the binary variable x1 to 1, xi to 1, then the corresponding value bi here is also a valid right-hand side value for that assignment. So then we can generate the following cut, where we are efficiently using independent right-hand side values, one for each partial integer assignment. Okay. So the first one I will refer to as single tightening, when we just reduce the right-hand side value as much as possible. The other one, multi-tightening, when we basically use different right-hand side values for different partial integer assignments. And here the multi-tighten cut, it can be a lot stronger than the single tightening. In the worst case, they are equally strong. But the multi-tighten cut, it has several very nice properties that unfortunately, due to the time limitation, I can't really dive into, but I recommend taking a look at the paper. Okay, so here's just an illustration of what the strengthening does. So we start from this cut with the single tightening, we move it inwards, and with the multi-tightening, we move it further inwards. So this gives us a significant strengthening of the continuous relaxation. Okay, and finally, just a quick word on some numerical results. So we tested this on problems with a suitable structure from MILP, where we have a different number of exclusive selection constraints. The disjunction size varied from 2 to 40, meaning that we consider between 2 and 40 binary variables that are included in an exclusive selection constraint, and different number of variables and constraints. So we tested this on a basic implementation of the ESH algorithm together with some primal heuristics. So we have a good baseline, and we use the same base algorithm together with the single tightening and the multi-tightening. And the result is that we obtain overall speed up with the single tightening, and we do a little bit better also with the multi-tightening. The single tightening reduces runtime by about 15%, number of iterations by 33, and the multi-tightening, I want to point out that it doesn't come at an additional computational cost, and it reduces runtime by 56%, and it reduces the number of iterations significantly. And what you can't really see from this figure is the fact that the stronger cuts here, they result in fewer iterations, but very importantly, it also results in easier subproblems. And by subproblems, I mean MILP problems here. And this is due to the fact that the MILP problems, they will have a stronger continuous relaxation. And by doing this tightening, there are several instances when we got a speed up of a factor of 1 or 2 orders of magnitude. And just to summarize what I've been talking about here, I hope to convince you that there is still room for significant improvements for Convex MINLP. I think it's exciting times now when companies such as FICO and Groby are also moving towards MINLP, and I hope to see great improvements. And the main takeaway is that we don't want to derive cuts only from the outer approximation. We also want to consider the nonlinearity. And we want to use multi-branch split disjuncts for lift and project type cuts, but we don't want to solve a cut generating NLP problem, at least not one based on the perspective formulation. And I think there's still plenty of room for improvement. How to do this, how to obtain these lift and project type cuts without solving a cut generation problem, this is an open research question. I don't have an answer to it, but I think this is a very interesting question. Thank you very much. And as a final word, I also want to say that I'm hiring postdocs. So if anyone is interested, please feel free to contact me. Thank you.
Okay, great. Thank you very much, Jan, for that talk. So I think maybe, Alex, if you're okay with that, we can take one question now, and then people can join the breakout rooms with either Sylvia or Jan and ask them more questions. So there's a question from Mark. What benefit can non-convex MINLP get from techniques along these lines?
It's an interesting thought, but I mean, the same concept still applies in non-convex MINLP. So I mean, you still there also care about getting an as strong as possible continuous relaxation. And I mean, then typically what you do is you start from a convexification of the problem, and you still want to derive strong outer approximation based from that. So it's difficult to point out exactly how to perform this, but these techniques are definitely useful also in a non-convex setting.
Okay, very good. So with that, we thank everybody for attending the talks, but please stay around for the next 30 minutes or so to socialize and also ask more questions to the speakers. So Alex will set this up shortly.
Yes, and stay tuned for announcements about next semester's season of DOTS. Thank you all for attending.